Oh, almost. No. Oh, no. Oh, there. No. Hello, Internet. My name is Quinn, and this is Blondihacks. I'm back on the big steam engine this week, and I'm going to make all of the upper valve gear. This engine is a piston valve or spool valve engine, which is a later design in steam engines that's a lot more efficient, but requires more precision to make. It's my first time building a valve system like this, so it should be fun. Let's go. Now, the kit actually came with stock to make the valve out of, which is where I'm going to start, but I lost and or used it for something else. But I have this other stock from the junk pile that should do the job. The diameter of a spool valve is extremely critical because this is effectively a ringless piston. So I'm taking extra care to measure the valve body there, make sure I know exactly how big it is and whether there's any taper in it and so on. So I'm measuring multiple places, multiple angles. I want a really, really good fit here. I'm aiming for about 1/1000th of clearance there because it needs to be pretty close to gas tight. But again, there's no rings in there and it has to still slide freely. I'll start, of course, by facing off the end, as is tradition. And because someone will comment, the orange corner there on the insert is to mark the dull one. It's not blood. Every time someone sees something orange or red in my videos, people assume it's blood. You people are very grim. There's no blood in my shop, just a lot of red oxide paint and orange nail polish. Everybody calm down. I'll get some tail support in there, which will of course be necessary, and now I can turn down the stock to a uniform diameter here. This piece of scrap had a bunch of random diameters on it, as scrap tends to do. So I'll start by roughing this down. I've got quite a ways to go here, but that's actually a good thing. The kit actually supplies stock where the nominal diameter is the final dimension of the spool valve, and I think that's kind of horsey talk because that relies on very good production values from the round bar, wherever they happen to source it from, and I don't know, I've never seen round bar that's consistently well produced enough that I'd want to use the final surface for a valve fit. So it's much better to have stock that's too large and turn it down to get a good finish and really, really nail that dimension. I took my time here because this is actually one of the most critical dimensions on the entire engine. This valve fit will determine a lot about how efficient this engine is and how well it runs. The valve body actually measured 1/1000th over size. My reamer got a little carried away apparently, so I'm aiming for basically right on size here, or a couple of tenths larger is okay. And I'm also checking for taper, of course. I'm 2/10 over all the way down, so I'm really happy with that. That'll be an 8/10 clearance, which is tight but will run in, and that's really what I'm looking for. And hey friend, don't let a dimension like that scare you off. You don't have to make these engines crazy accurately like this. It'll still run. It's just about how efficiently it will run and how much power it will make for how much fuel it's going to use. So don't be scared off by dimensions like this. I happen to get lucky and really nail this one, but you don't have to. Next, I found the end with my grooving tool here, and I'm going to move down and create a shoulder. This is a spool valve, and the name comes from the fact that it looks like a spool of thread or cable when you're done, so there's a narrow section in the center. Now, none of the rest of these dimensions on this valve are especially critical. There's generous tolerances on all of them, so I'm using the guessimeters. After establishing that first shoulder, then I translate down to where the second shoulder goes based on the thickness of the spool area, and then I turn this down to the same diameter. And then once those two shoulders are established, it's quicker and easier to come in with the turning tool and use that to turn out all the material in between. I said at the top that piston valves were more efficient, but you might be wondering why. Well, traditional slide valves used in the 19th century were advantageous because they were easy to make and they didn't have to be made very well. They only had a single flat surface, and the steam pressure in the steam chest presses the valve up against the ports, so you can make it with relatively primitive equipment that they had at the time and it'll still run well. The problem though is that steam pressure holding the valve against the face is costing you a lot of efficiency, and it limits how high you can go on the pressure because the valve gets pressed tighter and tighter and it gets harder and harder to move. Steam chests are also difficult to lubricate in the presence of superheated steam, which became much more prevalent in the 20th century. And there's some other ancillary benefits as well. A piston valve allows shorter steam passages and some things like that. So there's a lot of reasons here. There was a transitional technology called the balanced slide valve, wherein some boiler pressure was admitted to the inside of the slide valve to balance the pressure on both sides of it to relieve some of that friction. That was a cool little side quest in steam technology. I'm glossing over a lot of details here, but there's lots more to learn here if you're interested, so go to your local library. For the final pass, I bring in some light and I move in very, very slowly with that tool until I just see the barest wisp of a chip forming on the surface that the grooving tool left, and then feed across, and then I know that the turning tool will match the same surface there, and I don't feel any transitions there, so I think we're good. I got those little rat chaser rings there left over from where the two different tools met, so I'll cut those off and we are good to go. And there's another little shoulder at the end here, and this is a narrower shoulder, so for this one I just did a technique that you've seen me do before where I plunge in multiple times with the grooving tool to a depth that's about 5/1000ths short of the final depth, and then I can check the width of my shoulder area there just to make sure that's correct. In fact, it's a little bit wide, so I can move the tool over and narrow that up a little bit on my last pass. And then on the final pass, I go all the way into final depth and then pan across very slowly. And you can pan across with a grooving tool like this as long as it's a very light cut. This does two things for you. It leaves an excellent surface finish because it basically mimics the action of an old school shearing tool, and it evens out any variation that you might have in the grind on the end of your grooving tool. Like if there's a little bit of a curve or a little bit of an angle, panning across like that is going to eliminate most of that imperfection. Well, there's the outer shape of my spool valve. Pretty pleased with that so far. It's looking pretty sharp, literally, so let's go ahead and chamfer those corners. That will help it also slide in the bore a little easier. Now out with the live center, in with the drill, and I'm going to put a couple of holes all the way down the center of this thing. It starts with a small drill that acts as both a pilot and also is the registration bore for the valve rod at the far end of the valve. So we drill all the way through with this. And this is the very definition of a high aspect ratio hole, which is to say that the depth of the hole is many, many times greater than the diameter of the drill. So to keep the flutes from clogging up, you have to retract the drill frequently as you go. A quick way to do that is to simply release the tailstock, slide it back in until you feel the drill touch up, lock it, and resume feeding. Now that's not a good technique if you need a precise hole depth, however, so for that we'll do something different here, as you'll see, because every time you pull the tailstock back you lose your drill position, of course. Now we go in next with a larger drill, which does need to go to a very specific depth. It doesn't go all the way through. We need to stop just short near the other end. So I'm setting up a dial indicator on my tailstock quill here, and I'm preloading it all the way up to the final depth of the hole that I want, plus this feeler gauge here, which I'm using to find the end of the part for the drill. And then I just feed this drill into 0 on that indicator. I like to use this method because by feeding into 0, you don't have to worry about losing track of where you are, especially because when you need an accurate depth like this, you can't pull the tailstock back to quickly clear chips. You need to manually crank the drill all the way out, the old-fashioned way, and then clear the chips and then crank it back into where you were. So if 0 on the indicator is your destination, then you don't have to worry about losing track of anything. That is looking pretty nice. Now we're ready to part this off. So translate down, and unfortunately I didn't leave quite enough material right on the end there. So back in with the grooving tool real quick and make myself a little bit more space, and now I've got room for the parting blade. That large bore down the center, by the way, is actually the exhaust port of the engine, so you'll see how that works here in a little bit. But in the meantime, Yahtzee. Quick check on the length there, and that is looking good. Here's another look at the inside. You can see the shoulder formed by those two different drill depths, and you'll see how that translates into functionality in the engine here momentarily. I've got 2 cross holes now to drill in this, so I've got my cross drilling fixture, which I've shown a lot in previous videos, and this allows me to edge find on the fixture itself for the Y, and then I'll find the end of the part for X, and I'm going to spot 2 holes here on the top surface here. One very large one and one very small one. The very small hole goes first. This is actually just for a pin that holds the valve rod in place. The 2 quickest ways to break a small drill are to feed them too fast and to run them too slowly. If you look up the drill speed charts in Machinery's Handbook, For a drill this small, your mill almost certainly does not run fast enough. So run your mill as fast as you can and just feed slower than you think you should, and that will help prevent breaking the drill because the fact is that it's running too slowly. The other hole is much larger indeed. This is actually the exhaust port for the engine. What's neat about a piston valve engine is that there's only one port on the outside of the cylinder. That's the intake port for the steam. On a slide valve engine where you've got a steam chest, there's intake and exhaust ports plainly visible. On a piston valve engine, it's not exactly clear where the exhaust goes out. And what happens is the exhaust actually goes out through this larger hole and then up the center of the valve. So that's really cool, I think. Very, very clever. To deburr the concave edge that's created when you drill through a convex surface like this, it's a little tricky. I'm using a tip that my viewers gave me recently, which is to use a small round needle file. That actually does quite a good job. You can run it crossways across the hole like that to catch that edge. Here you can see how the large cross hole intersects right where that shoulder was created at the two different drills. That's why the depth of that larger drill was so important, because it creates this T-shaped passage where the steam can exit out the top of the valve. Okay, moment of truth. Let's see how this valve fits in there. I'll get some oil in there for a test fit here. And I'm looking for a fit that's very, very close, but will still slide. And I don't necessarily need it to slide very freely the way that a piston does. Like, it doesn't need to drop through, but it should slide very easily. And in fact, once I've got it moving in there, as I slide it back and forth, it loosens up slightly, which is a really good sign. The surface finish is there kind of already wearing in a little bit, and that is moving very freely. So I'm very pleased with that fit. I think we got that one. Let's do a quick steam science sidebar if you're wondering how this valve actually works. At the beginning of the cycle, the steam goes in through the intake port and into the big spool area of the valve, which is aligned with one of the steam ports. That pushes the piston down. And then as it's going down, the steam that was in the other side of the piston is pushed out that steam port, which is currently aligned with the area under the piston valve where that big cross hole is. So that steam gets pushed into the cross hole, up the center of the valve, and out the top of the valve body as the exhaust. Then when the piston gets to the bottom, the lower steam port is aligned with the spool area and the process reverses and continues. Now we need valve heads, and the kit supplies this stock for that. Valve heads are unique to piston valve engines, of course. A slide valve engine doesn't need heads on the ends of the valve because the valve is inside the steam chest. Now, because these are small parts and I've got relatively small piece of stock here, I'm going to use a classic trick, which is to make both parts at the same time on either end of the stock. The nominal dimension of the stock is already on size for the parts, so I'm just doing a very light skim cut to clean up the surface, basically the lightest possible cut that I can. That dimension there isn't critical. Next, I'm going to carefully square up the edge of the tool on the surface. And some light there will make sure I get it really right. I'm doing this because these parts have a registration shoulder on them, just like the cylinder heads do. But these are very small parts, and so the shoulder is equally small, and I can just create it with the edge of the turning tool here. So I squared up the tool as you saw to make sure I don't have any appreciable taper in this tiny shoulder. I roughed it in with 2 passes, and then because it's such a tiny shoulder, I could do the finishing cut all in one pass, just easing the tool in nice and slow until that shoulder was right on dimension. And I'll break that corner. Now I'm going to use the grooving tool to form the top of this head. Now this is the lower valve head, so I guess actually this is the bottom of the head, and it has a long skinny stem on the underside of it. So I'm effectively making the valve head inverted on the stock from how you might normally do, and I chose to do it this way because using that turning tool to create that accurate shoulder was much easier. If I make this head the other way around, which might seem more logical, then it's difficult to hit that diameter on that little shoulder. I'm not going to claim this was the best way to do it, but this is how I did it, and it seemed to work okay. Now I can center drill, pilot drill, and ream the center out here. This is for the valve rod to pass through, so that's why this is reamed. I just drilled deep enough such that when I part this off, it'll be all the way through. And then I chamfer those corners because chamfers are what separate us from the animals. Now I can flip this part end for end and create the upper valve head on the other end of the stock. This way I still have a way to hold on to both of these quite small parts. This was made the same way, except that the stem section, if you will, is very short and very thick, and that's because it has an internal pipe thread in it for the exhaust port on the engine. So I pilot drill that now, and that is it for the lathe work on these two parts. Now I can take it over to the mill and I can set it up in a collet block using the stock there that's between the two parts. So hopefully this strategy makes some sense now. This order of operations was chosen entirely around how I was going to hold this part for drilling the bolt pattern, and also making sure that I could use a turning tool for creating those accurate shoulders on there. Because this is a 4-hole pattern, it's very easy. I don't need the bolt circle feature of the DRO for this. It's just plus and minus the radius on either side after centering up with a gauge pin, as you saw there. With that bolt pattern done, then I just flip the part over in the collet block, center it up again with a larger gauge pin to match that hole, and do the bolt pattern again, and Bob's your uncle. Now over to the lathe once more just to part these guys off to the final length. Yahtzee, Yahtzee. Final step is to cut the threads. So for this I've got a scrap that I found in the bin that happens to have a bore in it the same size as those registration diameters, and I added a reamed hole the right radius away from that for a gauge pin that's going to act as a anti-rotation device, I guess. Anyway, then I'm going to use the tailstock die holder from my lathe over here in the mill, and I'm going to cut this thread like so. Now, if you look at these parts in the drawings, you would think, oh, it makes more sense to make them the other way in the lathe so that the thread is facing the tailstock and you can do the thread in the tailstock like you normally would for a part like this. I didn't do that just as I said because I wanted to be able to use the turning tool to create the accurate registration diameter on the far side. So this worked for me, but again, I'm not going to claim this is the smartest way to do it. Now I swap in the other part. This is a 1/8 NPT, National Pipe Taper thread. For this, I'm using my spring-loaded tap follower directly in the back of the tap there because it's got a center in it, and I'm just turning it with a wrench. As always with pipe taps, my strategy is to test fit until I get a good fit on a plug that I know is basically correct. So for that, I've got a boiler blanking plug here that has the right 1/8 NPT thread on it. The cool thing about pipe taps is that you kind of know you've got it correct if you can finger tighten it, but then you can't finger untighten it. You have to use a wrench to loosen it. And that's because the taper of the threads is locking together. That's how they work. I'm not a big fan of creating pipe threads, but it is really cool how they work. Next up is the valve rod itself, which is just a simple piece of brass bar stock that they give you with the kit. This just needs to be cut to length and have the ends cleaned up. We'll do a test fit on the lower valve head to make sure it's a decent sliding fit in there. As I said, I don't like using the nominal outer surface of round bar for a sliding precision fit like that, but this seems to work okay, so I guess we'll go with it. Then I stick that into the valve, and I'm using the cross pin hole that we made earlier as a drill guide to drill out the brass rod. The kit comes with a roll pin to attach these parts together, but that's a little bit too permanent for now. I'm going to be doing a lot of test fitting, so I turned up this little tool steel pin here to be a close sliding fit so I can easily assemble and disassemble this for all of the testing and stuff that we still have to do on this engine. Okay, let's put some pieces together. I've got the upper valve head there. It's a very close fit on there. We'll bolt that down. I'll be making probably studs and nuts for that at some point, but for now I'll use the Philister head screws from the kit. Then the lower valve head slides over the valve stem, and the whole assembly there goes up into the valve body, and then once again gets screwed into place. I'll do a little test here to see how well the valve moves. It's moving smoothly, but there is a little bit of a tight spot right at the bottom of the travel, which I think will run in, so I'm going to leave well enough alone there. You can make little adjustments here. If things aren't perfectly concentric, then this will bind up, so you can make the registration on the valve head a little smaller, you can file it down a little bit, you can make the valve rod fit a little looser in the valve, things like that until you get it running smoothly. Okay, well, we've got enough parts here that I can see if I can get some life out of the engine now. So I got my airline on there, and if you're skilled at this, you can, in fact, move the valve manually, and if you get the timing just right, you can actually get the engine running for a little while. It's not easy to do. It seems to be harder with a piston valve engine than it is with a slide valve engine, but with a little bit of practice here, well, quite a bit of practice, I spent some time fiddling with this, but I did eventually get the engine running briefly. There it goes. Look, and I lost it. Well, that worked well enough to know that this engine's definitely going to be a runner once we have the rest of the valve gear built. Well, there's all the parts of the upper valve gear. I'm very pleased with how those came out. There was some fitting and fiddling involved, but everything did come together, and it seems clear that the engine is going to run well once I get the rest of the valve gear built. That'll be coming up soon. Until then, thank you very much for watching, and thanks especially to my patrons for making this content possible, and I will see you next time.